And so today, what I'd want to talk about um, is essentially, move that over there, the relationship between kinetic theory about atomic and molecular relationships between pressure and temperature. All right. So real quick, just remember that pressure is really the force divided by the cross-sectional area that the force is being applied, right? So if you look at this image here, there's pressure being applied, and then that's gonna happen over an area. Now that area, it could be a circle or whatever, but when molecules collide against this surface area, like a rigid wall, the component of the momentum perpendicular to the wall is reversed, right? So what goes in comes out the exact same way, and the force is exerted on the wall, creating the pressure, right? So just imagine there's like little molecules, and I'm going to draw like a little, well, maybe we'll just search it up. We'll do molecules. This is what. And so I have like little molecules like this, very tiny ones though, not that big. And so they have kinetic energy. They're just vibrating around in space, and they crash up against the wall. Well, remember that molecules, when you have millions of molecules pushing up against something, it creates a force, and that air pressure, well, it doesn't necessarily have to be air pressure, but any pressure, a way that we can measure that force is by taking the force and dividing it by the cross-sectional area. If we expand on that and consider the momentum of that, right? So if we go back to our relationship between the pressure and volume, there's this interesting relationship where the pressure times the volume, and I'm not going to derive this, I'm just going to explain this, is equal to 1/3 times the number of molecules times the mass times the velocity squared, okay? And we'll just leave it at that for now. So P is the pressure, right, which is the average force per unit. V is the volume. N is the number of molecules in a container. Lowercase m is the mass of the molecule. And V squared is the average molecular speed squared. All right. Well, also recall that according to ideal gas law, that PV is equal to N, Boltzmann's constant K, times the temperature in Kelvin, right? So if these two are basically equal to the product of the pressure and the volume, then we can set them equal to each other. In other words, 1/3 N mv squared is equal to N Boltzmann's constant times the temperature T. Okay. And then if we do a little bit of algebra, right, we can use this relationship. We'll make that. Just make it transparent, and we'll give it. We could use this relationship to find some sort of connection between the velocity and also the temperature. So as the temperature, and just briefly, if you think about this mathematically, if the temperature increases, right? So if my temperature increases, mathematically speaking, the velocity increases, right? That V squared is going to go up too. Because the mass doesn't change and the number of molecules don't change, and this is Boltzmann's constant. So really the only two variables or parameters that actually change are the temperature and the velocity. And so there's a relationship between the velocity, the kinetic energy of the molecule, and the temperature. If you heat something up, it moves faster. If you move something faster by increasing the pressure or some sort of way, then you'll increase the temperature. Okay, so then let me slide down here. So what does that mean? Well, I'm going to put this object here. So if we think of this if you think of this makes the connections between great and small, between the molecules and the gas inside of a box. So this is let me label this so you know what I'm talking about. We're gonna zoom in. We're looking at the inside of a box here. Okay, and this is the best I could do. We're trying to zoom in and see what's going on right here. That's what all this stuff is right here. That's what we're trying to figure out. The gas in the box exerts an outward pressure on its walls. The molecule colliding within the rigid wall has a direction and a velocity and a momentum in the x direction, but then again it's reversed perpendicular to the wall. The components of the velocity and momentum in the y directions and the x directions are not changed. What this means is no force parallel. There is no force parallel to the wall. Okay, as it bounces into the wall, it's going to bounce out in a similar fashion that it bounces into. Okay, so if a molecule's velocity changes in the x direction, its momentum changes, right? So think of it like this. If I have a momentum in the x direction, it collides into the wall and it changes its direction. It goes in the opposite direction, if you want to think of it this way. Oops, I wrote that last letter down wrong. And if you don't remember, momentum, which is a lowercase p, is just m times v. That's how we measure momentum. All right? So then the change in momentum, if you think about that, this is the initial, this is the final, then the change in momentum is really the change in mv. And so then that could be written as mvx minus, right? So you could think of this as like the final, or this is the initial. It doesn't really matter. But you're going to end up minusing a minus, or you're going to be adding a plus. So let me think that through. Yeah, this would be the final, this would be the initial. And so you would end up with, let me think that through. If you start with this is the initial, this is the final. So this would be the final minus the initial. Well, either way, it'd be twice whatever the momentum is. So don't get caught up. I think technically, I apologize, but my if you think of going away from the box as being positive, because that's how they have it listed here, this is positive. So going into the box would be a negative direction. So I had to catch myself. Anyways, when you minus a minus, you actually get 2 mvx. So that's your change in momentum. You double the momentum. That's the change in momentum. So then also, remember that force is equal to the change in momentum over the change in time. So then we could say that 2 mvx all over delta t. All right, so let's keep moving. So then the force is equal to, shoot, I hate when this does this. Let me do this. The force is equal to 2mv sub x. And then if we think about this in terms of momentum, in other words, during the short time of the collision, the force of the molecule in the wall is relatively large, comparatively speaking. We are looking for the average force. We take delta t to be the average time between the collisions of this wall. It is the time it would take for a molecule to go across the box and back. So if you think of the distance, the time it would take would be 2L, right? So if you imagine this box and my little molecule bounces here, it's going to go all the way here and all the way back, and we'll call that length L. So 2L would be equal to the time at the speed, so that would be the time that we're interested in, delta t, and that would be at the speed of v sub x, essentially, okay? So then if and the relationship, remember that the rate times the time, right, Vx times delta t would be equal to the distance. Oh, shoot. Delta t would be equal to the distance, right, 2L. And then if I solve that algebraically for delta t, right, I get 2L, and I'm just dividing by Vx. Dividing by Vx. So then what I'm going to do is I'm going to sub down here 2L divided by Vx. Okay. And then if I clean this up a little bit, the 2's will cancel. The L stays on the bottom. We're going to toss this V up to the top. So then we get mVx squared all over L. Okay. So that's the force. And so then if we continue down this path, and I'm really just deriving that formula, and this is actually in the textbook. I don't know if I want to go through this whole thing. Yeah, let's just go through it, because all these steps will help you when you go to do your homework. So remember that the next step is, well, what's force and how does it relate to this stuff? Well, remember, this is going to be multiplied. This is just one molecule. So when we look at this here, we're really only thinking of one molecule. Well, the force in total will be this object times the total number of molecules. So the force applied times the total number of molecules would look something like this, okay? So this is one molecule. This stuff right here. This is in general, right? All right, so cool. We got all this stuff. So then the next step would be, if the bar over the quantity means the average value, what we would like is to have the force in terms of the speed velocity, right? Rather than the x component, right? So what does that mean? Well, remember that v squared is equal to the, shoot, I hate when that does that. The velocity in general, right, is equal to the x component squared plus the y component squared, okay? And if we think in terms of 3 dimensions, you could include the z component, right? But mathematically, that's what that is. And because they're totally random, and we're talking about the averages, right? Because they're all going to be moving in different spaces. So let's put that bar over that, because we're talking about the averages. So then, well, what does that mean? Well, we're going to assume that they're all going about the same speed. So then we can average this and basically say that they're all going about the same speed. So this velocity should be equal to this velocity because they're all going about the same speed, right? And this is a wild assumption, but yeah, if it's in a box and it's moving around in the box and they're bouncing off the boxes. So if those are all the same and you're going to add those up, you really end up with V bar squared is equal to 3 times V sub x squared bar. Okay, so what I'm doing is I'm deriving that formula. I probably should have done that first, but that's okay. And then from here, I'm just going to divide both sides by 3. And so then now I get that essentially V this is a lot to write down and do all at once. V sub x squared, the average of this, is equal to 1 over 3 V squared, the average. Okay? So now I'm going to take this, and I'm going to sub it in for this right here. So then my final thing is I get F is equal to N times M V squared over 3 times L, right? Because I'm multiplying that by 1/3. And then remember that pressure is equal to F over A. And so then that would give me remember the force is all this stuff, right? And mv squared all over 3L, right? But I've got to divide that by the area. So I'm going to tack on the area. Well, your length times your area is really a volume, right? So then this becomes NMV squared all over V. And then what we do is we're gonna oops, I didn't want to do that. We're gonna tack in, I'm gonna try to throw it in here. Let me see if I could do it. I don't know if I could do it. Let me see. Oh shoot, I'll just write it in there. We're gonna put that 1/3 in the front. And so I did all that, right, so that you could see this relationship. And so then if you multiply that out, you multiply both sides by V, you get PV is equal to 1/3 NMV squared. And that's where we started at the very beginning, way up here. I said I wasn't going to derive it, and then I was thinking about it, and I decided to derive it. So that's where this comes from. And then this relationship is going to be important. Now, the reason I derived it is in your homework, you might need to know and think about that, right? A length times an area is a volume. That's an important thing, okay? So anyways, I've got that relationship. Well, here's some more stuff. Remember also that kinetic energy of an object, I hate when that does that. So the kinetic energy of an object is equal to 1/2 times the mass times the velocity squared. That's a V, right? And if that's the case, we also know that that could be in terms of energy, and this is the part that you may not remember, 3/2 times Boltzmann's constants times the temperature. Okay, so remember also that this is a kinetic energy of a molecule. This is the kinetic energy of a molecule, but this can also be the thermal energy of a molecule. And we did this towards the end last year when we were talking about, and we should have reviewed it in the other section, but that's the thermal energy of a molecule. So then if we look at that, we can connect the two, right? In the sense that they're both equal to kinetic energy. So what does that mean? Well, if I take this 1/2 mv squared and I set it equal to 3/2 kT, and remember this is kinetic energy. This is the molecule's motion. And this is the thermal energy. So the energy is the energy, all right? If I multiply both sides by 2, right? If I multiply this whole thing by 2, I get mv squared is equal to 3 kT. So what I'm going to do is I'm actually going to solve for the velocity. So I'm just going to divide both sides by m, divide this by m, and I get v squared is equal to 3 times Boltzmann's constant all over m. Take the square root of both sides, and I get that v, which we'll call VRMS because we started off by assuming that these were averages, is equal to the square root of 3 times Boltzmann's constant all over m. And so where does all that come from? Well, if we go back up here, all the way at the very beginning, we would get a very similar connection here, right? Do you see how if I took this, this equation right here, I'd end up with the same thing basically. The ends would cancel, right? I'd have to divide both sides by m, I'd multiply by 3, and then I'd take the square root to get the velocity by itself. And VRMS just means root mean square speed. We'll talk about that later. So now that I know that relationship, let's do an example problem of that, right? So let me take a picture of this example. So let's calculate the kinetic. Whoops! Oh, I just went bonkers, huh? Let's calculate the kinetic energy and speed of a gas molecule. So here's what we have. What is the average kinetic energy of a gas molecule if it's at 20 degrees Celsius, and then find the RMS of a nitrogen molecule N2 at room temperature? Okay, so that's what we're going to do. Let me move this over a little bit so we can see it. I'll move this over too. Okay. All right, so the first step in this process, I have to decide what I'm going to do. Okay. So I've got to convert the temperature, right? So we have the temperature T. Oops. The temperature T has to be converted to Kelvin. So I'm just going to say 20 plus 273, right, is equal to 293 Kelvin, 293 degrees Kelvin. That's important, okay? So now let's figure out this, the energy, right? So because I have a temperature, I just need to find the kinetic energy. But remember that the kinetic energy is equal to the kinetic energy of the thermal. So really, because they've given me a temperature, I could just plug that in and find the thermal energy, and it'll be the same as the kinetic energy. And then we'll use that information and work backwards to find the velocity. So how do I do that? Well, 3/2 times k times t. Remember that Boltzmann's constant, k, is equal to 1.38 times 10 to the negative 23, and it's joules per Kelvin, joules per, running out of space here, Kelvin. Okay, so then I have 3/2 times 1.38, I'll write it a little better here, 10 to the negative 23 joules per Kelvin, right? And then we multiply that by the temperature of 293 Kelvin, right? Remember that Kelvin and Kelvin cancels out, so then my final answer will be in joules. This will cancel with this, and then my final answer will be in joules. Well, if I crank through that, I find that the kinetic thermal energy is equal to 6.07 times 10 to the negative 21 joules. Okay. Now remember, this is thermal, right? This is the thermal. This is thermal. But thermal is equal to kinetic, so it's also the kinetic. They're the same things. Kinetic. I don't think I needed to put that extra C. Let me take that out. Somebody will see this and be like, "Excuse me, you have the wrong one." Okay? So that's that. But now I want to know the velocity. Well, to do the velocity, we just figured out our equation, right? But we said that the velocity, it's this thing right here, right? So the average velocity, or root square mean, it's kind of like an average, is equal to the square root of 3 times k times the temperature all over the mass. The mass is the challenge, right? That's why they told us we had a diatomic molecule, right? So how do I figure that out? Ooh, I know K, I know T. Okay, so the mass is a little more challenging. To find the mass, so let's do that. Mass of the diatomic molecule for nitrogen, I'm going to have 2 atoms, right? If we look that up on the periodic table, and let me show you guys this. Periodic table. So nitrogen is right here, okay? So our atomic mass is 14.007, so we're going to use that, but there's 2 of them, right? And what does that mean? Times 10 to the negative 3 kilograms per moles. And this is interesting because it's really in grams, right? So remember that your atomic mass is how much something weighs in grams if you have a mole of it. But now we've got to convert the moles. So we have to use Avogadro's number on the bottom. We got to divide by this to cancel out the moles. So there are this many 10 to the 23rd. Let me rewrite that a little better. Times 10. That's so annoying, frustrating. frustrating. And so there's this many particles per mole, but we would write mole raised to the -1. And so essentially what this does is this converts everything. The moles cancel, and then we get our mass in kilograms, which seems like a lot, but not really. So you get used to doing this stuff. So 4.65 times 10 to the -26 moles, or kilograms, sorry. Whew. So we did all that to find this value. Okay, so that's the mass of 2 nitrogen. It's very tiny, okay? 2 nitrogen atoms. All right, so let's plug it in. So to find the velocity, this is the tough part. My velocity, RMS, root mean square it just means that we did the square and the square roots, right? So that's what that means when we say root mean square. That's that the v squared equals vx squared plus vy squared. Or that's how you calculate it. So remember, the formula is 3 times Boltzmann's constant times the temperature all over the mass. So then this is going to be 3 times 1.38 times 10 to the -23 joules per kilogram, or per Kelvin, sorry, times 293 degrees Kelvin divided by 4.65 times 10 to the -26. Okay. And then when you do all the math on that, it's actually going to give you an answer in meters per second, which is kind of cool. And I'm not going to spend a lot of time explaining that. Check the dimensional analysis if you want to. You're going to have joules. You're going to take the square root of joules, but I feel like I'm forgetting. Oh, kilograms. So joules divided by kilograms, and do the math on that. It ends up, everything cancels out and you get meters per second. Okay? So that's how fast, based on the temperature, that's how fast those molecules are moving. Okay? That's just one example. And so obviously as you increase the temperature, right, so let's look at that a little better. You can have molecules moving around. The arrow represents the velocity vector. If you increase the temperature, they'll move around more because they'll have a higher kinetic energy, which means they have a higher thermal energy, which translates into a higher kinetic energy, right? So, and so there are many molecules moving so fast in ordinary gas, they could collide billions of times every second. Individual molecules do not move very far because they're just bouncing into each other. And then disturbances are kind of similar to like sound waves that are transmitted at speeds, and this is all done at the molecular level. So they're constantly pushing into each other. Now, the one thing that I want to talk to you about is that you can also, you have a distribution or a probability of these molecules and their speeds. So there's the maximum velocity based on some information. This is at 300 Kelvin. So I don't know, whatever, what's that, 27 degrees Celsius or something like that. Or yeah, that's what that is. That's where you get the peak velocity. RMS is kind of like, like the average or whatever. But this is, I don't know how to describe this. Maxwell-Boltzmann distribution, which is what you're seeing here, of molecular speeds of an ideal gas. And then most likely the speed Vp is less than the RMS speed. Although very high speeds are possible, only a tiny fraction of the molecules have speeds that are on the an order of magnitude greater than VRMS. So this is the probability or distribution of all the molecules contained in something. This is actually referred to as the Maxwell-Boltzmann distribution. So what they did is they came up with this distribution. They calculated different velocities at this temperature. Distribution. And so this is usually pretty good enough for most calculations. Obviously, you would use calculus and stuff to make a better calculation. The distribution of thermal speeds depends strongly on temperature. As the temperature increases, the speeds shift higher. Here's another example of this, so let me show you. So I had an interesting conversation with, I was doing research at Notre Dame one time and a PhD candidate. We were talking about stuff, and I said to him, I said, everything in the universe is dynamic. Everything changes. It's not perfect. Nothing is really linear here. So if you have a temperature, at a higher temperature, you could see that the distribution shifts a little bit, right? And there's some reasoning for that, but just as the temperature increases, you could see that probability distribution changes. And that's the main thing that I want you to see here. So it's not always exactly fitting to this curve. As the temperature changes, so does the distribution. That's why in this distribution they define what the temperature is. So the distribution can shift or change, and this is based on there's some calculus involved for this, but this is a little more dynamic. This is what really happens in the world. Now, if you're doing graduate level research, you have to consider all these things. Okay. For the AP exam, you might need to know the difference. So I'm going to do one more example if I have time. And this one's kind of a big one, but I think we could get it done. All right, so let me just do this. So on this one, we're being asked to calculate the escape velocity of helium atoms in order to escape Earth's gravity. An object near the top of the atmosphere, an altitude of 100 kilometers, must travel away from Earth at 11.1 kilometers per second. And so that's just based on escape velocity, okay? This speed is called escape velocity. In other words, once you obtain this speed, Earth's gravity, the acceleration due to the gravity, or the acceleration due to Earth's gravity, has no impact. It can't slow you down enough to stop you from leaving Earth's atmosphere. At what temperature would the helium atoms have a RMS speed equal to this escape velocity? Okay, so what they're saying is if we heat up some helium atoms, so this is very similar to the problem that we just did. So we know that we're going to need to know the mass. Well, remember that the mass is the molar mass of what we have. This is when we did this last time, but I'm going to write it out because I was thinking about it. And I said, I should probably explain that. And then the number of atoms per mole. Okay, and then we got, so again, we know that the kinetic energy has two relationships. One, there's the actual kinetic energy, that's the velocity of the molecules, right, is also equal to the thermal energy. Which is based on the temperature. We also know that there's a relationship, right? We said that V RMS is equal to 3 times Boltzmann's constant all over the mass. Well, they're asking us what is the temperature. So we've got to find the temperature. They give us the velocity. The velocity is equal to 11.1 kilometers per second. Okay? And we know everything else. Well, we got to calculate the mass, right? So if I take this equation and I solve for t and I do a little algebra, I get t is equal to the mass. Well, do I derive it? Yeah, let's just derive it so you guys aren't, the derivation is helpful. So the first thing I'm going to do is I'm going to square both sides, because I got to get that t out. So then I get v squared, and I'm not going to write RMS every time. I'm just going to write velocity squared is equal to 3kt over m. I'm going to multiply this by m over 3k, because that way the m cancels with this m, and then 3k cancels with this one. But remember, whatever I do on one side of the equal sign, I have to do to the other. So what I end up with is I end up with mv squared divided by 3k, Boltzmann's constant, is equal to the temperature I need. Okay, cool. Helium, this is the part that we have to do. So before I can get back to this, I got to find the mass of helium. So remember, if I look this up on the periodic table, our molar mass for helium is 4.026, that little number in the right-hand corner. So I'm going to say 4.0026 times 10 to the third kilograms. Remember, everything has to be in kilograms. Our molar mass is given to us in grams, so we have to do this conversion per mole divided by Avogadro's number times 10 to the negative 23 moles. Okay, when I do that, I get 6.65 times 10 to the negative 27 kilograms. That's the mass of a helium molecule. Well, I say molecule because usually helium is diatomic, but we're going to let it slide because it asks for one atom only. So anyways, so that's the mass. So let's plug that in. So I'm going to use this formula here, right? So I'm going to say 6.6, in other words, the temperature equals 6.65 times 10 to the negative 27 kilograms, that's my mass, times the velocity, which is given in kilometers, but if I convert that, how many meters are in a kilometer? 10 to the third meters per second. But remember, we have to square that. Divided by 3 times Boltzmann's constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. Okay, and so then what's my final temperature? And this is given in Kelvin. 1.98 times 10 to the 4 Kelvin. Okay, so that helium atom has to be pretty hot, right? So this is hot. This is the temperature that I need for that helium atom to escape Earth's atmosphere. Now the temperature is much higher in atmospheric temperature. And so they just ask us the temperature, but there's a little blip here in the book that says that the temperature is much higher in the atmospheric temperature, right? Which is approximately 250 degree Kelvin, which is about negative 25 to negative 10, negative 25 degrees Celsius to negative 10 degrees Fahrenheit. And so very few helium atoms escape Earth's atmosphere. Gravity just pulls them back down. The only way that it would get, it has to literally get this hot, which is pretty hot. Okay? And that's it for the notes.